over there. So we've got a ray of light coming in here, and it gets refracted. Now, because this is actually parallel, you actually find that it's this line over here, this incident ray over here, and this one over here. These will actually be parallel. If I extended this out like that, that will actually be parallel to that, but it diverges in and it changes. So it repeats itself. Just one moment, and then I'll leave time for questions at the end. Okay, so we've got our formula, our Snell's law formula. If we remember what that is, our Snell's law formula. This one over here. We've got this one over here. N1 over N2 is equal to sine theta 2 over sine theta 1. Okay, so we're going to use that formula there. Alright, so we got N1 over N2 is equal to the sine of theta 2 over the sine of theta 1. Now I think what you were saying, Tina, is what we're going to be looking at now, is that you've got to decide what is 1 and what is 2. Alright, so if we're looking at this situation over here, you've got to look at this formula relates to one boundary going from one change to the other change. So if this is your N1 here, this will be your N2 here, this will be your theta 1, and this will be your theta 2. The angle that you're dealing with always goes between the ray, this is the light ray coming in, and the normal. Alright, between the light ray and the normal, that is your angle. Yes, Namso? Okay, now when you go from, we had that little discussion about the car to show when you slow down, you always bend towards the normal. So when you go from a lower to a higher optical medium, it always bends towards the normal. When you're going from a higher to a lower, it bends away from the normal. But the very important thing is that you always deal with the angle related to the normal. Okay. Yeah, so I mean, this one over here is going to be, if this is theta 1, this would also be theta 1 over here. The reflection, you get what we call partial reflection. Those are always the same. But this is when you put this into our formula. So let's just say this refractive index over here is 1.4. We say that this is air. If we say this is air, so this is equal to 1. Let's just say this is 34 degrees. Alright? So to work out theta 2, we're going to get 1 over 1.4 is equal to the sine of theta 2. That's what we're trying to work out. We're trying to work out the refracted ray divided by the sine of 34 degrees. And so it's a very simple calculation. The sine of theta 2 is equal to a sine of theta 34 times 1 over 1.4. Can somebody just calculate that for me, please? Anybody got a calculator handy? What do we have to be careful with though when we got to make sure that we're in degrees, not radians. I mean the standard thing is always radians in your calculator, so you got to make sure that's in degrees, and then you just do the inverse sine once you get your value there. Your theta 2 should be obviously less than 34 degrees. What do you get? Then you've got to do the inverse sine of the answer, 23.5. So we're getting about 24 degrees there. 24 degrees that you're getting. Okay. So it's a very straightforward formula to use. Now, if I went out here, now let's say we're doing the reverse. Now we're going out and we want to work out what this angle is, because by your parallel lines, this angle over here, this is 24, this would be 24 degrees. And now your N1 here would equal 1.4. All right. Your N2 would equal 1 because now you're going out and now you're trying to work out your theta 2. So, you just put that in and you should get coming out here around about 34 degrees because this was a bit of an approximation, so it will change it slightly. Okay. Yeah.